In this video, we'll see a simple type of conditional random field known as the linear chain conditional random field. So we motivated the use of conditional random fields in the context of sequence classification, where we want to be able to jointly model the full sequence of labels associated with a sequence of inputs. So this here is essentially another way of writing the probability of a given value for y1 up to y capital K, where capital K is the number of elements in the sequence, given the first input in the sequence up to the last input in the sequence. Now let's look at how we will a particular parameterization of this conditional distribution. So perhaps the most simple conditional random field, or CRF, is the linear chain CRF. Now let's see what we do in the context of a linear CRF. Now, in regular classification, where we don't assume there is any dependence in our model between the adjacent positions in a sequence, in this context, it means that our distribution, the probability that our model assigns to a particular sequence y given a sequence of input x, will just be the product of the probability that our neural network assigns to each label yk given its associated input xk. Now, in the neural network, the way we model this is that we take the softmax output activation function. So we take the exponential of the pre-activation value for the label for which we are evaluating a probability, that's yk. And then we divide that by normalization constant, or partition function, which is just the sum of all potential values of the numerator. So this would just be the sum of the exponential of the pre-activation function for any value of yk. And now we're taking the product of this because we're assuming our model does not model dependencies between adjacent positions in the sequence. And now because the product of the exponential is the exponential of the sum, we can also write this as the exponential of a sum over positions k of the pre-activation at the output layer for each label yk as predicted. So the pre-activation as computed based on the associated input xk. And then we also divide by the product of the partition functions or normalization constants here. Now in the linear chain CRF, in the context of sequence classification, we'll essentially add a term that will also express a preference for particular sequences or pairs of adjacent values for yk and yk plus 1 for any position k. So in other words, the conditional distribution of y given some sequence x is going to be the exponential of, again, so here and here we have exactly the same term. So this is essentially saying how we think yk, the particular value of yk for which we're evaluating a probability, is likely given the input and given the associated input xk. So that's why we have xk here. Plus another term which is going to say how much our model likes that yk is followed by yk plus 1. And this, so how much we like seeing yk followed by yk plus 1, is going to be parameterized by a matrix V, where its entry yk plus 1 tells us how much we like this particular sequence of yk plus 1. So just to be clear, yk plus 1 is a variable and it has a particular value. If we have 10 classes, then yk could be 1, 2, 3, up to 10. And similarly, yk plus 1 is also a variable, but it's the variable that represents the label at the next step, k plus 1, and it also takes a value from 1 to 10. And so vyk, yk plus 1, if yk for in this sequence here, if yk was equal to, say, 5, and then yk plus 1 was equal to 3, then this term would, for this particular value of k, would look at the entry at the 5th row and the 3rd column of matrix V. Okay. So to sum up, in a linear chain conditional random field, we keep the per position term that expresses how much we think yk should be likely given its associated input xk. But we add another term which also expresses a preference as to whether we like seeing yk followed by yk plus 1 for a particular position over position k. And then notice that here also we sum from k equals 1 up to k minus 1. So we add our preferences for each position k. So if we had a sequence of size, say, 3, and then we had that we're evaluating the probability for y1 equals, say, 2, and then y2 equals 5, and then y3 equals, let's say, 3, then it means that this term here would correspond to, I'll write it just here, would correspond to v2 5 plus v5 3. Okay, so if we were to compute this expression, and actually this part of the expression for these values, for this sequence of y's, then I'd have this term plus this term. So to sum up, the probability of a sequence y given x is going to be the exponential of a sum of terms which express a preference about the value for each element in the sequence yk in the sequence of labels given the associated input, plus the sum of pairwise preferences between adjacent labels. And so the probability is going to be proportional to the exponential of the sum of these two types of terms. And now because we want a probability distribution that sums to 0, we have to divide by something we call the partition function, or sometimes people use the name normalization constant. It's a partition function in particular because it depends, for one thing, on x, but it also depends on the parameters of the model. So for different parameters, we'll get a different value of this normalization constant. And what this z is here is really just the sum of the numerator, but over all possible sequence values, so all possible values of that sequence y. So there's actually a number, an exponential number of such sequences, and so a naive method for computing it would be intractable, but we'll see in future videos how to actually write a dynamic program for computing the partition function for a linear chain conditional random field. Now visually, if we look at the flow graph for computations, so before in the regular neural net, from the input we'd get a computation graph up to the pre-activation layer, and there would be no interaction between this computation for, say, the input at position k minus 1 and the computation of the neural net at position k. That would compute the pre-activation for that particular input. Now, what we're adding is a matrix of undirected connections between adjacent positions, such that the such that essentially the probability we'll assign here will also depend on the on what's computed here, and so on. And so this is very informal. This is just to illustrate the dependencies here, and this is sort of an informal graph of computations, but we'll formalize this a bit more in the next videos. What's important to realize is that between each adjacent step, we always use the same matrix V as our set of parameters that control the interaction between that essentially control how we model observations of adjacent labels in the sequence. So the matrix V here is the same as this matrix, and so on. And similarly, the set of weights of my neural network, so the matrix W here and B here, and also all the parameters that would be between the input and the pre-activation at the output layer, these parameters for this neural net is the same as these parameters and as these parameters. So it's sort of the same copy of the same neural network, with shared weights. And so this will have implications when, for instance, we compute gradients. It means that we'll get gradients that will affect, so the gradients, when we do backpropagation, there will be gradient that will go on this matrix here, which is the same as this here, so we'll have to accumulate gradients for each position. Okay, but this is just to really highlight the fact that we're using the same neural network for each position, and between adjacent position, we're using the same matrix of parameter V. All right, so that's the linear chain conditional random field.